Here, we are going to solve a puzzle which consists of these four squares given to us. These two squares are identical. This square, you can see, exactly fits the two of them. So its side must be twice, that is 20. And the side of the last square is not known. So this is an unknown square. And on top of these four, they have superposed a triangle. You can see the vertices of these triangles are lying on the vertices of some of these squares. And we are supposed to find the area of this triangle. Now, if we look at the formulae that we know for finding the area of a triangle, okay, there are two. One is area is equal to base into height divided by 2. If we try to use this, let's see if we know the base. Well, we know one side for sure because this is 10 and 10, this is 10 root 2. But how about the height? The height of this triangle is not known because the top point lies on an unknown square. So another formula, say Heron's formula here, which uses the so-called semi-perimeter, which is nothing but half the perimeter of this triangle. So if you know the sides A, B, and C, use this formula. But we don't know this side, neither do we know that side. So we are in a fixed path. So whenever that happens, you feel that some problem is really impossible, try to change the perspective. So that is what we will do. We'll just take this triangle, rotate about this point so that this known side, okay, which we can use as the base, becomes horizontal. Why? Because we are usually familiar with triangles with base as a horizontal line, and we have now made not only the base horizontal but some diagonals of these squares, say this diagonal of this square, or the mid-sized square's diagonal here, or the large unknown square's diagonal here, they have all become horizontal. And how does that help? Well, that will help us in finding the height. Okay, the distance between these two horizontal lines, these two parallel lines, is going to be the height. And because these two lines are parallel, it gives us a freedom of taking this top vertex of this triangle and moving it anywhere along this horizontal line. Because when we do that, see, the height has not changed, neither has the base changed. So although this triangle has changed the shape, it hasn't changed its area because both base and height have remained the same. And therefore, now we have a freedom of keeping this top vertex at the most convenient point that we can choose on this line. So I say let us keep it here. Why? Because that point is on a mid-sized square that is completely known. So we can find these dimensions now. Number two, it completely squeezes out this large square which was unknown. Now that is completely out of picture. It is not contributing anything to the dimension of this triangle. So we are in good shape now. So let us go ahead and work out the height and base. The base is going to be 10 and 10. So this is 10 root 2. Similarly, the height is going to be, this is 20, this is 20. So it will be 20 root 2. And if we substitute those two values in this formula, base and height, we are going to get 10 root 2 into 20 root 2 divided by 2. These two square root 2's will multiply to 2 in the numerator, cancelling with the denominator, and we are left with just 10 multiplied by 20, giving us the area of 200 square units. So that's the answer to the puzzle.